with that, then we will go ahead and get started. As I mentioned, we're going to cover the 3, 4, 5, and 6 tonight. And so let me screen share the first one with you. So this is kind of this is a continuation of what we learned from in the last couple of class periods, or especially in the two Mondays ago, when we started our journey into chapter 3, where we were looking at applications of differentiation. So this section, we're going to now expand upon that. And now we're going to look for absolute maximum and minimum values, right? So previously we looked at, all of the other things like the domain and the range. And we've looked at, where where we might have asymptotes and all of those different things. So we're just expanding upon that now, right? And so basically we have, in this section, we're going to find absolute extrema, and we'll do that by using the maximum minimum principles, number 1 and number 2, okay? And so a relative minimum may or may not be an absolute minimum, right? So we've talked about relative minimums. We can have more than one relative minimum, just as we can have more than one relative maximum. That's just talking about basically where we have peaks or troughs in our in our function. So an absolute minimum, though, is the smallest value of the function over the entire domain, right? So you can think about that as, if it's the absolute minimum, it is the very smallest of the small values. Similarly, a relative maximum may or may not be an absolute maximum, because the absolute maximum is the very largest of the function, the largest value of the function over that entire domain, okay? So that's kind of what that definition, that first definition gets at. Then we move into theorem number 7, where we're looking at the extreme value theorem. And this really is just saying that if you have a continuous function that is defined over that closed interval, and we know it's closed because of the brackets, and that interval goes from A to B, so any value from A to B, right? Those are where you are on the x-axis, and they must have an absolute maximum value and an absolute minimum value if we're going over a closed interval, okay? And then we'll move into theorem 8, which is our maximum minimum principle number 1. And so essentially, this is telling us that if we're looking on this closed interval, if we find the derivative, okay, and then we determine the critical values, we can list out all of the critical values as well as our endpoints. So sometimes our critical value might be an endpoint, and that's okay. But so you'll see here, we've listed this as A, C1, C2, all the way to Cn, and B. So that's telling me it's my 2 endpoints and all the critical values that fall between those endpoints, okay? So we want to list those out, and then we want to evaluate our function at each of those points, right? So we're going to substitute in our leftmost endpoint, plug that into our original function. What value do I get? Plug our first critical value in. What value do I get? Basically, that's saying when I plug this value in for x, what am I getting out for y? And we do this for all of the endpoints and for both of the endpoints and all of the critical points. Typically, you're only going to have 1, maybe 2. Sometimes you might have 3 critical points, But in the examples we're going to do and your exam, you will probably only have one or maybe two critical values and then the two endpoints, okay? So when you do that and you get those values, then your largest value for that f of whatever, so our largest y gives us an absolute maximum, and the smallest value will give us an absolute minimum. So that really is the gist of that theorem number 8, where we're looking at that max-min principle number 1, okay? And we'll see this in action here in a moment. Any questions just about the theorem itself? Okay. And so lastly, the theorem for the max-min principle number 2, there will be time when we have exactly one critical value for our function, in which case we can then evaluate that for the second derivative. If the second derivative is less than 0, then we have an absolute max. If the absolute value is, not the absolute value, if the second derivative evaluated at that critical point is greater than 0, then we'll have an absolute minimum, okay? And so here I've listed out for you kind of a strategy as to how we would want to go about finding an absolute maximum or minimum, okay? And so in that case, again, kind of along the lines that I mentioned in when I was talking about principle number 1, is first we want to find the derivative, and then we'll find all the critical values. And now we get to an if statement, right? So if the interval is closed, and that's very important, the interval is closed, that's the next two steps, right? But for number 3, if the interval is closed and there is more than one critical value, we have to use the min-max principle number 1, okay? If it's a closed interval and there is exactly one minimum or one critical value, then we can use either minimum principle 1 or maximum principle number 2. And then finally, if the interval is not closed, for example, infinity, negative infinity to infinity, or 0 to infinity, or a to b, but notice there's parens on all of those, okay? And the function only has one critical value, then you have to use the min-max principle number 2, okay? Any questions? All right, so let's look at some examples. So for this first problem, this is on page 314 of your textbook. And our instructions here ask us to find the absolute minimum maximum values of each of the functions over the indicated interval and indicate the x values at which they occur, okay? So this is telling us our interval is from -1 to 0. It is closed because we have the brackets, okay? So if we follow along with the steps that I kind of laid out on the previous slide, the first thing we want to do is find the derivative of our function. So the derivative here is 3x squared minus 2x minus 1, okay? The second thing we want to do here is critical values, right? So this is our critical values. And if you remember, to find a critical value, we really just want to set our derivative equal to 0 and solve. Since the derivative exists for all real numbers, we can do that, right? Remember, if the derivative is restricted because maybe there's a x in the denominator or something like that, and it's not, and you can't take the derivative across all real numbers, then you wouldn't have any critical values. But in this case, it's a linear function. There's no restrictions on what value x can be. So we can go ahead and solve that as 3x squared minus 2x minus 1. Set that equal to 0 and solve. If we factor this, we get 3x plus 1 and x minus 1, right? So one of those two have to equal 0. So either 3x plus 1 equals 0 or x minus 1 equals to 0, in which case this is x equals negative 1/3, right? We've minus 1 from both sides, then divide by 3. And this one would be x equal to 1. So we have two critical values here, right? So our critical values are x equal to negative 1/3 and x equal to 1, right? Now, if you think about this, though, I'm going to put a little side note over here. So our critical values are negative 1/3 and 1. However, 1 is not in our domain, right? It's not in that interval, right? So it is not part of the solution. It would not be a critical value. So it is not in the interval. So not included. I'll put that here. Okay. Just as a little side note. Okay. So when we list out, so step 3 has us listing our critical values and endpoints. So we're just listing critical values and endpoints. Okay. So we know our endpoints are negative 1 and 0. So we have negative 1 and 0, and we want to fill in our critical values in where they fall in between that, right? And so that's going to be the negative 1/3, and then we have that 0. So we've listed all three of those here. Again, remember, x equal to 1 is not in our interval, so we don't count that critical value down here as a potential. Okay. Now we need to evaluate. Okay, so we're going to evaluate f of x at each value in step 3. And so we have f of negative 1 is equal to negative 1 cubed minus negative 1 squared minus negative 1 plus 3. And that becomes, it simplifies down to 2. Okay. Do the same for our next point, which is negative 1/3. So we have negative 1/3 cubed minus negative 1/3 squared minus negative 1/3 plus 3. And that is 86 over 27, which is approximately 3.2. Okay. And then for our last point is evaluating at f of 0. So that is 0 cubed minus 0 squared minus 0 plus 3, and that equals 3. Okay. So now we want to determine what is our absolute max and what is our absolute minimum, right? And so we'll see here the largest value is 3.2, right? So we have this value of 3.2. So this here is going to be my, I'm going to have an absolute maximum at this point. Okay. Then I can also see that at x equal to 1, that is the smallest, right? So this one is the absolute minimum. Okay. Question. So our absolute max occurs at x equal to negative 1/3, and it results in a value of 3.2. Our absolute minimum occurs at -1, and it results in a value of 2. Okay, question. Okay, so the next problem, this is problem number 32 in our textbook. The directions here are asking us to find the absolute extrema of the function, if it exists, over the indicated interval. It also wants us to indicate the x value at which each occurs. And then when no interval is specified in these problems, like in this problem here specifically, then we're to use the real numbers, which is negative infinity to infinity. Okay, so that's telling us here, because there was no interval given, we're to use negative infinity to infinity as our interval. Okay, so we proceed as in the previous, right? So the first thing we want to do is take our derivative. So f prime of x is going to equal negative 0.02x plus 1.4. Okay. Again, this is linear. So f prime of x is exists for all real numbers. Therefore, we can set our derivative equal to 0 and solve to get our critical value. So this is going to be negative 0.02x plus 1.4 equal to 0, minus the 1.4 from both sides, then divide by the negative 0.2, and you get that x is equal to 70. Okay. So in this case, because remember, let's go back over here to the rules. If it's not closed, and we have this situation here where we're looking at negative infinity to infinity, we have to use minimum maximum principle number 2, which it's actually on this slide. That is telling us we have to do the second derivative to determine the maximum and the minimum. Okay, so now we need to come over here, and the next thing we want to do is let's calculate our second derivative. So our second derivative then is just negative 0.02. When we take the derivative of the first derivative, that's what we get, right? And so now we're going to evaluate this at our critical value, and that is negative 0.02, which that is less than 0, right? Because there was nothing to substitute the 70 into. So it doesn't matter what value our x is, our second derivative is always going to be negative 0.02, which is less than 0. Therefore, we have a maximum at x equal 70. Okay, so now let's evaluate our function itself at 70. And so that's going to be negative 0.01 times 70 squared plus 1.4 times 70 minus 30, and that gives us 19. So what that tells me is the absolute maximum is 19, which occurs at x equal to 70, and there is no minimum value on this graph. Okay, questions? All right, so the last example from this section is number 58 in your textbook. This one is a life science practical example, and this has to do with your blood pressure. So with the dosage of X cubic centimeters of a certain drug, the resulting blood pressure in millimeters of mercury is approximately given by this formula here. And we want to find the maximum blood pressure and the maximum blood pressure and the dosage at which this occurs. Okay. Now, what we're given here is that we're asked for, and so this is something to pay attention to, right? When you're doing problems and you get word problems, if you notice here, we're asked to give a dosage in cubic centimeters, but our problem was given to us in millimeters, right? So we need to adjust that. So this B of X formula is in millimeters, and we want to just change that to centimeters, okay? So we'll change that formula, and so when we're going from millimeters to centimeters, but mind you, we're doing cubic millimeters to centimeters, right? So in this case, we would end up, this would become so small that it's negligible, right? So we can, it becomes much closer to where it's almost zero. So we can just wave that away. And so for this one, we're going to move our decimals, right? So we're moving our decimals 2 places. So 0.5, it's close enough to 0. It doesn't impact our thing. So we can just say that this is like 305 x squared minus 1830 x cubed. And this is in centimeters, okay? So again, like previous ones, the first thing we really want to do is take the derivative of that. So when we take the derivative of this, that's b prime of x. Excuse me. And so 302 times 2 gives me 610. So that's 610x minus 5490x squared. So we can see that the derivative exists for all real numbers. There's no restrictions to it. Okay, so b prime of x, we could set that equal to 0 and solve. So for this case, let's factor a 610x out of both terms. So we have 610x. If we take that out of the first term, that leaves us with 1. If we take 610 out of 5490, that leaves me with 9, and there was an x squared. We pulled 1 out, so it'll leave me with an x, and that equal to 0. Okay, so we have these two terms, and either 610 is equal to 0 or 1 minus 9x is equal to 0. So divide both sides by 610 here, and I get that x is 0. I can add 1 to both sides, divide, minus 1 from both sides, divide by -9, and I get x is equal to 1/9. That's approximately 0.11. Okay, so I have to look at, so let's look at our endpoints here for our problem. So our endpoints are on the interval, because see, the equality tells me that I get a bracket. So my endpoints are 0 and negative 0.16. So now in my third step, I need to list my critical points and endpoints. And so my endpoints are 0 and 0.16. And my x, I already have 0. I don't need to list it twice. I only need to do it once. And then this would be a critical point that I would put in here. Since my one endpoint is negative is a fraction, we can put this endpoint here as 0.11. You could also use 1/9, that's fine too, put it in there and then get a decimal approximation at the end. Both are equally acceptable. So the last thing we want to do is, because we have a closed interval, we can use the minimum maximum principle number one, which tends to be the easier of the two because we don't have to do a second derivative. So we can now apply this, evaluate our function at the endpoints and critical values. So plugging 0 back into our original equation, we get the 305 times 0 squared minus the 1830 0 cubed. That's going to give me a value of 0. When we plug in the 0.11, that gives me 305 times 0.11 squared minus 1830 times 0.11 cubed. That's going to give me a value of approximately 1.255. Okay. And then when we evaluate at our endpoint, our rightmost endpoint, we get 305 times 0.16 squared minus 1830 times 0.16 cubed. And that's approximately 0.312. Okay. So this problem asked us what is the maximum blood pressure and the dosage at which it occurs. Okay, so we come and we look at this table here of values, and we can see right here, this is the maximum. Okay, that is our maximum blood pressure. And it occurs, it is this 1.26 with a dose of approximately 0.11 cc's of the drug. Okay. Question. All right. So let's look at chapter 3.5. This is a section on applications, and we're looking at optimization in business, economics, and then just general applications. Okay. So we get a new theorem here, and that tells us that the maximum profit occurs whenever we have X values at which they're like this, right? So when you think of the profit function, right? My profit is going, think about it in business terms, right? My profit is going to be my revenue minus my cost. Okay. And so in these practical examples, it's no different. So I'm going to have a maximum profit occur when I look at this and I can determine if the derivative of my revenue is equal to the derivative of my cost, right? Or I can look at the second derivative of it. I want my second derivative of my revenue to be less than the second derivative of my cost. Okay. So in this section, this is a lot along the lines of, like, if you ever had the opportunity to take an elective. Nova itself doesn't offer an operations research course, but there are at universities, there are an actual entire class dedicated to operations research. And that actually has a lot to do with, you want to maximize your profit, minimize your costs, and you get all these constraints and things like that to apply to it, right? And so we're going to look at this at a very high level view where we're going to have our objective function is to either maximize something or minimize something, and it's going to be subject to or such that you'll see here, and we only have one constraint typically. Okay, and so, but again, if you moved on and ended up taking like operations research, you may have 2 or 3 constraints that would add to the complexity of the problem. So for the purposes of this class, we're going to look at things with only one constraint, but our objective function may be either maximizing or minimizing. Okay. So for this one, we're going to look at a maximized problem. Okay. It is on page 328 of your textbook. So if you're following along, and it is number 10. Okay. So for this one, we really just want to maximize z equals x times y, where x and y are both positive numbers, such that 4/3 of x squared plus y is equal to 16. Okay. So first, we want to express our z function in terms of one variable, right? Do you know how to do a derivative with 2 variables? It's much more complex, right? And so in this case, let's go ahead and express. So the first thing we'll want to do is let's express our z function in terms of one variable. Okay, so how do we do that? Okay, first we want to solve our constraint our such that value to only one variable. Okay, so first solve for y. And so that is, we have 4/3 x squared plus y equals 16. So when we, excuse me, when we solve for y, we're really just moving all of this to the other side. So we get that y is equal to negative 4/3 x cubed plus 16. Okay. Then we want to substitute y in for z up into our function, into the y portion of our z function. Okay. So then substitute for the y in z equals x times y. Okay, so that is z is equal to x times y, but we're subbing in negative 4/3 x cubed plus 16. Okay, and so that is going to simplify. We're just distributing this x to both terms, and that will simplify to negative 4/3 x. This is an x squared, sorry. I don't know why I wrote an x cubed. So this becomes negative 4/3 x cubed plus 16x. Okay. I'm going to rewrite this because I personally prefer to have the positive first. So that's the same as 16x minus 4/3 x cubed. Okay. Either way is correct though. All right, so next I want to find my derivative of z. So z prime is equal to, and we're going to just do it here. So that would be 16 minus 3 times 4/3 is going to give me just this negative 4x squared. And that set that equal to 0. This is 4x squared equals 16. Divide both sides by 4. I get x squared equals 4. Take the square root. And I get that x is equal to plus or minus 2, right? But remember, x must be positive. So we're only going to choose the positive one. Okay. So now, since there's only one critical value, we can use the second derivative to determine whether we have a maximum or a minimum. Okay, so I'm going to bring that up over here since I ran out of paper. So number 3, let's look at our second derivative, and that is negative 8x. Okay, so we'll apply z double prime, that's our second derivative, applying that at the positive 2. And so that's negative 8 times 2, which is 16. 16 is greater than, I mean, actually it's negative 16, so it is less than. So we have negative 16, which is less than 0. Okay, so since the second derivative is negative, that means we have a maximum. Okay, so we have a maximum at x equal to 2. So the last thing we want to do is evaluate our function at x equal to 2. So we have our function evaluated at 2 is going to give us 16 times 2 minus 4/3 2 cubed. Okay. And that will simplify to 32 over 3. Thus, the maximum value of our z function is that 60 is going to be actually, sorry, this doesn't simplify. This simplifies to, that's going to be 32 minus 32 over 3. And that is 64 over 3. So for x equal to 2, that occurs at, so we do our y equals this here, 16 times, sorry, I already did that step. We have the 16 times, or 16 minus 4/3 times 2 squared is going to give us, that's our, just our original up here. And that would give us a y value equal to 32/3. So in this case, we are going to have an objective. So this is our maximum value, right? Our maximum objective value. And it occurs at, when we plug back into our, let me do another color. So we have our y value here. So when we plug that into here, we have y equals negative 4/3 times 2 squared plus 16. And that will give us a value of 32/3. So our objective function, here, right, is this, because this is our objective function that we've simplified it to, right? So when we plug in that value in, the x value into that, we get what is our z function maximized. When we plug that 2 into our y, our such that equation, it tells us where our maximum value occurs for our x and y combination. Okay. Question. Okay. So this next problem is a pretty interesting application problem. where we want to, it's number 16 in your textbook, and we want to maximize the area of a particular thing, right? So in this case, we have a rancher that wants to enclose 2 rectangular areas that's near a river. He wants to be able to have sheep on one side and cattle on the other. Okay. The problem is the rancher only has 240 yards of fencing available to him. So he wants to know, he comes to you and asks you to help him determine the largest total area that he can build to enclose these 2 spaces. Okay. And so luckily there's a water side, so we don't have to put fence on the water side. We only need fencing on the outer perimeter and then some fence between the sheep's pen and the cattle's pen. Okay. So in this case, there's a few things that we can look at. First of all, when we're wanting to talk about area and perimeter and things like that, we really need to know our length and width, right? So if we let x equal our width, okay, you can see here we have x, x, x. That's how wide it is, right? Here, here, and here. So we're going to have 3 times the width, right? So we have that much fencing, and whatever that value is, we need it 3 times. Okay. And then let's let y equal our length. Okay. And so that would be this piece right here. How long is that? Okay. All right, so once we have that bit of information, we can determine perimeter. If you remember back to probably just, maybe high school or algebra days, maybe geometry, perimeter is if I just added all of the sides up, right? So in this case, if I'm looking at my perimeter is going to be 3x's plus 1y. Okay. And I know that that has to equal, no, it has to be less than or equal to 240 yards of material, right? Because I can't put more fence in than I have material to build it. Okay. So I can write this. Remember how we did the last one? We wanted to, let's write this in terms of one variable. So I could say that that's the same as saying y equals 240 minus 3x. So all I've done here is rearrange that equation. Now, something else is that x and y are greater than, they must be positive. Okay. Because I can't build a negative amount of fence, right? And so we can see here then that we can either have 0 to 200, and so x can be, it can't be 0, so notice there's no equality there, but it can't be, and it can't be greater than 240. So I'm on this interval from 0 to 240 where I don't actually equal 0 or 240. I could just get close to that. Okay. Question. So this problem was asking us to maximize the area. Okay. So what is area? Area is really another equation. This is our think of this as our z function from the previous example, right? So our area is equal to our length times our width, right? So area is just length times width. Okay. So in this case, we would say that our area formula is x times y, length times width, right? So we can then substitute in what we know about y. So this is x times let me go ahead and put this in blue here so you can see that that 240 minus 3x is coming from above. Okay, we already calculated that. Okay, so when I simplify this, I get 240x minus 3x squared. Okay, question. Now I want to take the derivative. So when I take the derivative of a, I end up with 240 minus 6x. Okay. The derivative exists for all x's, therefore I could set it equal to 0 and solve. So when I do that, I get 240 minus 6x equal to 0, and I get that x is equal to 40. So there's only one critical value on the interval. So I need to do the second derivative test to determine if I have a maximum or a minimum and what that value is, right? So when I do my second derivative, I get that is, so the second derivative here is just negative 6. Okay. And that is less than 0. So that tells me that I have a max. And I have that max at x equal to 40. So I can determine what my y value is at 40. And I'm going to move this. I thought I was out of paper. So let's move that down here. So I can determine what my y value is, right? So the things we need to know. So when x equals 40, then y equals, and we're just pulling the blue equation. So right? So we have this right here. And so that then equals 240 minus 3 times 40, which equals 120. Okay, that's my y value. Now I want to evaluate my a at 40. Okay, and my a prime at 40. Wait. Oh, no, we want to, not our a prime. We want to just go back to our original function here, right? So let me, I want to make this here a different color so I can pull that out for y'all. Let's just do purple. So our a function is this right here. So we're going to copy that function and then plug in 40 for our x, right? So that's 240 times 40 minus 3 times 40 squared. Okay. And so this is 4,800. Okay. Therefore, we have a maximum area of 4,800 yards squared. So max area equals 4,800 yards squared. Okay. When the overall dimension are 40 yards by 120 yards. Okay. Questions? So if you were advising this farmer, you would say, hey, you should make the purple line up there in the picture 120 yards long. And each of the 3 red ones, you should make 40 yards long. That would then, if you added that up, right? If you did 40 plus 40 plus 40 plus 120, you would use all of the 240 yards of your material. Okay, questions? Okay, let's look at another example from this. Now in this case, instead of maximizing, now we're going to minimize. Okay, and so surface area, just as a refresher, surface area of an open top square-based rectangular box is found by adding the area of the base and the four sides. Okay, so the area of the base, you can see the base then is going to be here and here. So the area of the base, x squared, is the area of the base. Okay. And then each side is going to be x, y would be each of these sides. So you have x, y is the area of the sides. Okay. And there are 4 of them. Okay. So our surface area, which is S is our surface area, that's going to be x squared plus 4xy. Okay. Now, this problem also wants us to, so if we're looking at this, it gives us what the volume of the box is. Okay. So that's something else to keep in mind. So I'm going to move this just over to here. And volume is equal to our length times our width times our height. Okay. So in this case, my length is going to be x. So my length will be x, my width will be x. So we have x times y. So that's really x squared times y. Okay. And furthermore, it tells us that that volume is 62.5 inches cubed. Okay. Now to express our S function here in terms of one variable, let's just solve this for y. Okay. So this is the same as saying trying to think the easiest, less confusing way to. So if we just do our volume first, right? We want to solve that for y. Then we can just divide both sides. So if we divide both sides by x squared, right? This gives us a function y is equal to 62.5 over x squared. Okay. So when we plug that into our S function, equals x squared plus 4x times 62.5 over x squared. Okay. So the one of the x's in the denominator will cancel with one of those, and we're left with x squared plus 4 times 62.5 over x. We can actually 4 times 62.5 is going to give me 250 with over x, but I'm going to just move that x up here so it's x to the negative 1. Okay. Question. So S is defined only for positive values. So we minimize S on the interval of 0 to infinity. Okay. So our interval is 0 to infinity. And again, that is because S is only defined for positive. We can't have a negative surface area. Okay. I'm going to add another page in here so we can have more writing space. Okay. So now what we want to do is let's take our S prime of X, okay, and that equals 2X minus 250 X squared. Actually, X to the negative squared. Let's go back and look. Yeah. Okay. So our S prime is 2X, and then this would be minus 250 X to the negative 2. Okay. So that's our derivative. Now let's write that in terms of just where our exponents are positive. So that's 2X minus 250 over X squared. Okay. Since our derivative exists for all X's on that interval, right? Because our interval is from 0 to infinity with the paren on our 0. So it wouldn't be restricted here with the denominator because it's not in our domain. Then we only have the one critical value. So we can, I'm going to make that a little clearer. Separate those. Okay. So we can set our S prime equal to 0. And so that would be our 2X minus 250X to the negative 2 equal to 0. And when we solve that out, we end up getting that X, we get 2X equals 250 over X squared. And then we also get, simplifying that even further, multiplying both sides by X squared, we'll get that X cubed is equal to 125 because we'll divide the 2 by both sides. And so we can say that the X is equal to 5 then, okay? And since there's only one critical value, we use the second derivative to determine whether we have a minimum there or not, okay? So our second derivative here is S double prime is going to be just 2 minus, actually it becomes plus, right? Negative 2 times negative 250 gives me positive 500. And then this is X to the negative 3. So we can rewrite that as 2 plus 500 over X cubed. Okay, so now let's evaluate our second derivative of that X. So we have S double prime evaluated at 5. So that's 2 plus 500 over 5 cubed. Okay. And so that's going to be 6, which is greater than 0. Since the second derivative is positive, we have a minimum at X equal to 5. Okay. So we want to find our Y value when X is equal to 5. So Y then, we want Y when X equals 5. So let's go back to the previous page here and we can copy our Y value function. Paste that in here. So our Y value here, and we want to substitute in 5 for that. So we get 62.5 over 5 squared. And so that's going to give me a value of 2.5. Okay. So the surface area is minimized when X is equal to 5 inches and Y is equal to 2.5 inches. So we can tack on the inches here if you want. the diameter or the units. So now we can find the minimum surface area by substituting those two values back into our original equation here, our original surface area. Okay. So we plug that back into here, and we end up with our x is 5 squared plus 4 times 5 times 2.5. And so that is going to give me a value of 75. So the minimum surface area is 75 inches squared when the dimensions are 5 by 5 by 2.5. Okay, so we would have dimensions are 5 inches by 5 inches by 2.5 inches. Okay, question. Okay, one more example. This is number 28 out of your textbook. This one, we're looking at maximizing profits, and we want to find the maximum profit and the number of units that must be produced and sold in order to achieve that profit. We're going to assume that revenue and cost are in dollars, and that X is the number of units for which we're looking at. Okay, so this one is problem number 28. We are given that our revenue function is 5x, our cost function is the 0.01x squared plus 1.2x plus 60. Okay. All right. So now, when we look at this, we know that our profit is equal to revenue minus cost. Okay. So our profit is revenue minus cost. So let's figure out what is our profit function. So that is 5x minus 0.001x squared plus 1.2x plus 60. So we have to distribute this negative here to the entire cost function. Okay. And so that is going to give me a value of, so when we simplify this out, it's negative 0.001 x squared plus 3.8x, because we have the positive 5x minus 1.2x, we get 3.8x, and then minus 60 because we're distributing that negative there. Okay. And we will look at this and know that our profit can be 0 to infinity, right? So 0, our x can be 0 to, well, we can't ever equal infinity, because if we think we're at infinity, there's another value even larger out there. So you can't actually ever be equal to infinity. It just keeps getting bigger, right? So, but we can't equal 0. We can have no profit at all. That is if we break even, right? If our costs equal our revenue, then we break even, we have no profit. So we can have equality there, but we can't actually make an infinite amount of profit. There is limit. Okay. So now let's determine what is our derivative here. So our derivative of our function is negative 0.002x plus 3.8. Okay. the derivative exists for all values of x in our domain. And our domain is, let me put that here. So this means our domain is 0 to infinity. Our profit function derivative is good for all of that. So we can set our profit function equal to 0 and solve. And so that gives me negative 0.002 x plus 3.8 equal to 0. Therefore, x is equal to 1900. Okay, so there's only one critical value, so we have to use principle number 2. And so we'll look at our second derivative. So our second derivative here then is going to be just negative 0.002 when we take that second derivative. And that is less than 0. So since that is negative, that means we have a max at x equal to 1900. Okay, so we'll plug in our p of 1900 back into our original equation, and we get negative 0.002 times 1900 squared plus 3.8 times 1900 minus 60, and that equals 3550. So the maximum profit is $3,550. So max profit equals $3,550 when 1900 units are produced and sold. Okay, question. All right, so that is all of the section 3.5 material. Let's go ahead and take a 10-minute break. So let's take 12. It's 8:08. So let's come back at 8:20 p.m. and we will finish out section 6. It shouldn't take us too long, maybe 20, 30 minutes. It's about the same length as each of these previous 2 sections, or about half an hour at most in lecture, but we will do that when we come back from break, and then we'll remain around if you have questions on any of the material we've covered thus far. Okay, so we'll come back at 8:20. All right, it is 8:20, so let's go ahead and finish with tonight's lecture. And we'll finish up with chapter 3, section 6. This section begins on page 233 of your textbook in case you're following along. In this section, we will use calculus to make approximations, and we will find marginal costs, revenue, and profit. Okay. So what you're looking at here on the screen is just some definitions. I'm not going to go over each of them, as the formula is the same. It's just solving it based on whether you're looking at cost, revenue, or profit. So I'll walk you through, though, the marginal cost one. And that basically just says that when you have x, and x is given by c prime, right? That's the derivative. That is the approximate cost of the x minus first item. So if I look at my derivative, that's really the cost of x plus 1 minus the cost of x. So what does it cost me to produce one more widget? Okay. And so that can be approximated by my cost function evaluated at x plus the derivative of my cost function evaluated at x. And it's exactly the same thought process for your marginal revenue and your marginal profit. Okay. All right. So here, a couple of just little formulas. So the first one up there is for some function f, which is a continuous function, and its differentiable function, and there's a small change in x. So when you see that triangle there in front of x, that means change in x. You might hear it referred to as delta x or change in x. But this really is, when you think of that, that is how much change is there in my y, or how much change is there in my x. Okay. So when we're looking at this change of y over change of x, that should be very familiar to you, because what do we do when we're determining a slope, right? That's y2 minus y1 over x2 minus x1. And so all that is my change in y over my change in x. Okay. And so we can say then that when we have our change in y, that we can say that, so the second definition down here, when we have y is equal to our f of x, right? We've done that substitution many times through the course of this semester. But we can define d of x, that is the differential of x, by dx is equal to the change in x, right? And our differential of y is the change in our y. Okay. And so what we do is here, we can, so it's the same if we do our dy, right? So dx or dy ultimately is really just that change. Okay, any questions? All right. All right, so let's look at a couple of examples. So if you are following along, page 341 of the textbook. So for this first problem here is, we're looking at f of x is equal to x squared, x is equal to 5, and then we have the delta, and then the delta is 0.3. Okay. So when we're looking at this, we first want to evaluate, this at x plus our change in x, okay? So f evaluated at x plus our change in x. So that's going to be 5 plus 0.03, and that equals 5.03, okay? So we're going to evaluate our function. That is, our function is x squared. So that equals 5.03 squared. And so that is 25.3009. Okay. So when we evaluate just our function, f of x, right, that is going to be f of 5, which is 5 squared, which is 25. Now, when I want to determine what is my change in y, my change in y is my f of x plus delta x minus my f of x, right? So no different than if we were doing, if we were just doing to like the slope of a line or something, okay? So this is part A. So it's a 3-part thing on this problem. So when I do this, I end up with 25.3009 minus 25. So my change in y is 0.3009. Okay? Questions? All right. So the second part of this problem, so part B was we were looking to change a y for the given x and y. So the second part is so part B, we're given, they want us to take dy equal to f prime of x dx. Okay. So for this one, we have, if we divided both sides here, if we get rid of this dx, right? That leaves us then with dy dx is equal to f prime of x, which is what we've been doing, right? In the past, you saw sometimes I would write dy dx, sometimes I would write just f prime. They're the same thing, but now we're kind of tying it all in and seeing why exactly it is how it is, right? Or how we've been doing it, okay? So that would be, so in this case, we have we have we would have dy dx equals 2x, right? We're just taking the derivative here of our original function, okay? And we can then translate this to say then that dy equals 2x dx, okay? And the reason we're peeling that dx off is because in the next chapter, in chapter 4, we're going to start, we're going to move away from differentiation and we're going to move into integration. And this will become more of a key role, is really how do we undo, so we kind of have to reverse engineer. An integral is really just reverse engineering what the derivative was, right? So I have the derivative, and now I need to reverse engineer to get back to my original function. Okay. And then finally, we can look at part C of this. And part C of this is asking us to take dy for the given x and dx values, right? So in this case, it would just be, we have dy equals 2x dx. And so that gives me 2 times my x is 5 and my dx, or change in x, is 0.03. When I multiply all of that out, I get 0.3 is what my dy is equal to. Okay, question. All right, so let's do the same thing for this next example, okay? Same page, just problem number 8. So we have f of x equals 2x minus 3, x is equal to 8, and our change in x is 0.5. Okay? And then, so same process. We want to we want to first solve for f of x plus change in x. We have f of x plus delta x, and that equals f of 8 plus 0.5, and that is f of 8.5. Okay. So this gives me, if we look at our function, right, that was 2x minus 3. So we can say then that that's 2 times 8.5 minus 3, which is 14. Okay. So now looking at our f of x by itself, we're just evaluating that at f of 8. So that is 2 times 8 minus 3, and that equals 13. Okay. Now we want to look at what is our change in y then, and that is really just our f of x plus change in x minus f of x. So this is 14 minus 13. So our delta y is 1. Okay, so that's part A. Part B is our dy dx is equal to 2. Therefore, we can say that dy equals 2 dx. Okay. And part C, we have dy equals 2 dx. We're really just taking this, moving it up, substituting in what we know. And we know that we don't have any x's, so we are just at 2 times my change in x, which is 0.5. Therefore, my dy is equal to 1. Okay? Questions? Anna, you unmuted. Did you have a question? All right. So now we're going to move into some examples like numbers 14 through 18. And for this one, it's asking us, it wants us to use the change in y as approximately the derivative of x times the change in x to find the decimal approximation of what's under the radical, right? In each case, it wants us to select a convenient value for the y value before calculating f prime and of x and the change in x. Okay. So in this case, what we're going to do is they're giving us this radical, right? So we have to say, okay, let y equal f of x, okay? And our function here is the square root of 8. All right. Well, 8 is not a perfect square. So let's let x equal to the closest perfect square to that. And that is 9, right? 9 is a perfect square, so let's choose 9. So what is the difference between 8 and 9, right? Because actually this is the square root of x here. If I put a 9 in here and I wanted to get back to my original, then my change in x is equal to 1, right? I would need to take what's under the problem I was given, add 1 to it, and that's how I get to 9. Okay? So what would my change in y be? My change in y is my derivative of x times my change in x. So my derivative is, that's going to give me approximately 1 over 2 square roots of x delta x. Okay, so that is approximately 1 over 2 times the square root of 9 times 1, right? Subbing in the x equal to 9, delta x equal to 1. And so that is approximately 1/6, or in decimal form, 0.167. Okay. Now we can approximate the square root of 8. We're going to approximate that and say that the square root of 8 is equal to the square root of 9 minus delta y. I do want to point out, I chose this minus here. This minus is because the square root of 8 is less than the square root of 9. Okay, we'll see in a moment. In another example, we'll make that positive because what we choose is greater than what our original is. Okay. All right, so now we have the square root of 9 is equal to 3 minus our delta y. So this is 3 minus 0.167. And so this is an approximation of 2.833. Okay. So if you take out your calculator, right, your 5 decimal approximation of the square root of 8 is approximately 2.82843. Thus, our approximation is reasonably accurate, right? We did an approximation of 2.833. If we had a calculator and took the square root of 8, we would get negative 2.82843. Very similar, right? But this process, we may not always have a calculator that can do square roots, so we need to be able to have a process that we could do those approximations without a calculator. Okay, you won't have to do this portion of the test without a calculator on the exam, but you may have to do a problem like this where you have to walk through the steps of it. Okay. Question. All right, so let's look at the next example. This one is a cubed root. Okay, so in this example, we want to let y equal f of x, which is equal to the cubed root of x. So we know that 28 is not a perfect cube. If we go up to 29, no, 30, no, 31, no, and so on. So let's go negative. If I do, or minus 1, if I look at 27, that is a perfect cube. That's 3 times 3 is 9, times 3 is 27. Okay, so let's let x equal 27. And so my delta x is equal to 1. The difference between those two is 1. Okay. All right. So now we are looking at this and we have our delta y is equal to our f prime of x delta x. So that's approximately 1 over 3 cubed root of x squared times delta x. Plugging in our x and y values that we have assumed, we get 1 over 3 cubed root of 27 squared, okay, times our delta x, which is 1. So this gives me approximately 1 over 27. And that's approximately 0.037. Okay. So that's our delta y. Now we want to approximate the cubed root of 28. Okay. And that is equal to the cubed root of 27 plus delta y. So like I gave you guys earlier, this here is, I'm going to write it in the same way I did that. So this is the cubed root of 28 is greater than the cubed root of 27. Okay, so that's why we've chose this here to be positive. Okay, the cubed root of 27 equals 3, and my change in y is 0.037. So when we add those together, we get 3.037. So similar to how we did this other example here, if we looked at the 5 decimal approximation of the cubed root of 28, so you could put that in your calculator as 20, this would be the same as putting 28 raised to the 1 divided by 3 to get it to the cubed root. And you will see that that value is 3.03659. Thus, our approximation is once again reasonable, right? So 3.037, if we just looked at the 3 decimals, is exactly the approximation we got by our calculation. Okay? Question. So a couple of word problems here. So the first one here is number 20 in your textbook. Well, it's not really a word problem, but so for this one, it's another where we need to do some approximations. This one, we want to let g of x equal x cubed. We want to find the linearization of g at a equal to 4, okay? So in this case, we have to think back to our linear approximation. And so for part A, we would say L of x equals, or L of x of g at a equal to 4. That's what it's asking us here for, is going to be, we'll evaluate g at 4. And so that is 4 cubed, which is 64. And let's look at g prime evaluated at 4, and that is 3 times 4 squared, which equals 48. Okay, so then our linear approximation is our function evaluated at the first plus f prime of a times x minus a. Okay, so that gives me a value of 64 plus 48 times x minus a. Okay, except our a, we can actually plug that in, that's 4 as well, right? So we were given that as part of question A. So when we simplify this, we end up with 64 plus 48x minus 192. All we've done is distribute that 48 to the parentheses. And finally, we'll combine any like terms, and we end up with 48x minus 128. Okay? Any questions so far? Now in part B, okay, part B, we will take our linearization to approximate 3.9 cubed, okay? So L at 3.9 is equal to 48 times 3.9 minus the 128. So that's 59.2. Okay. So instead of doing 3.9 times 3.9 times 3.9, we can use this linear approximation and figure it out that way. Okay. But if you put 3.9 cubed into your calculator, you should come really close to that value. Okay. All right. So now we want to use that calculator, right? That's what part 3 is. Find what 3.9 is using the calculator. And so when you plug 3.9 cubed into the calculator, you get 59.319, which is pretty close to that linear approximation that we got in part B. Okay. So the last step then is part D. It wants to know what's the difference between the approximation and the actual value. So we would take our approximation, 5.9. Actually, we want to know the difference between our actual and the approximation. So it's 59.319 minus 59.2. And that's 0.119. So the approximate is 0.119 less than the actual. Okay, so it's 0.119 less than the actual. Okay, question. All right, let's look at our last example here. Our last example is we're looking at marginal profits, and we want to do this for Sunshine Motors. And they have a weekly profit in dollars for selling X amount of cars. Okay. And that formula is given there to us as P of X. Okay. And currently 60 cars are being sold per week. So we want to determine what is the current weekly profit, what is the marginal profit at 60 cars, and we want to use that marginal profit to estimate the weekly profit if we increase our sales to 61 cars. Okay. So the first one, part A, we really just want to look at P of 60. We want to evaluate our function at 60. I'm not going to write out all of those, but it would be negative 0.06 times 60 cubed minus 0.2 times 60 squared, and so on, finishing out filling it into that original equation. And so the profit would be $50,784. Okay. So the second thing is we want to, in order to do our marginal profit, we need to know what the derivative is. So P prime of X is negative 0.018x squared minus 0.4x plus 900. So when we solve or evaluate our derivative at 60 cars, then that is going to be $811.20. So the marginal profit is $811.20 when 60 cars are sold each week. Okay, question. So finally, part C, it wants us to know what is, we want to use the marginal profit to estimate the weekly profit if we get one more car, right? So that is my profit of 61 cars is approximately my profit of 60 cars plus the derivative of 60 cars. Okay. So that is approximately 50,784 plus 811.20. And so my estimated profit for selling 61 cars per week would be $51,595.20. Okay. Question. All right, that is all of the new material that I have for you all this evening. If you don't have any questions, you're free to leave. If you do have questions, I'll stick around for a couple of minutes or as long as I need to get those answered.